Hello everyone and welcome to our channel, Mootechie. A special welcome to all the dairy technologists and students joining us. This is Class 8 in our Dairy Engineering series, a direct continuation of our last lesson where we discussed bottle washers. Today we are moving on to another critical sanitation topic, cleaning in place, or CIP, systems and their design. We begin our discussion on cleaning in place, or CIP, and the design of these automated systems. First, let's understand what CIP replaced. Manual cleaning involved scrubbing tanks and vats by hand and hosing them down with water. This method had significant disadvantages. It was very time-consuming, expensive, and often failed to achieve a proper bacteriological clean. Because of these drawbacks, manual cleaning has been largely replaced by mechanical and automated cleaning systems. So what is CIP? CIP involves the circulation of cleaning liquids through machines and other equipment in a closed cleaning circuit. A high-velocity fluid creates a scouring effect that dislodges dirt deposits. If water velocity alone is insufficient, detergents are used to enhance the cleaning power. Not all equipment can be cleaned with the same CIP program. Several factors determine what can be cleaned together. First, the product deposit must be of the same type. Second, the cleaning surface materials must be the same. And third, all components in the circuit must be available for cleaning at the same time. Achieving efficient CIP requires specific knowledge. You need to understand how mechanical, thermal, and chemical processes work on different types of deposits. This includes knowledge of how acids and detergents affect these deposits, including the correct detergent type and concentration. The goal is to optimize the interaction of all these elements for the best cleaning results. A key concept in CIP is fluid dynamics, specifically turbulent versus laminar flow. Turbulent flow has a flat velocity profile and a thin boundary layer at the pipe wall, which makes it very effective for CIP. In contrast, laminar flow is a streamlined flow where the velocity is faster at the center of the pipe. This creates a thicker boundary layer and is ineffective for CIP, as it does not provide the necessary scouring action. Now let's talk about flow in more detail. For effective CIP, we need turbulent flow, which is achieved when the Reynolds number is greater than 3000. The goal is to minimize the boundary layer, which is the laminar layer on the internal pipe wall. There is a minimum CIP velocity required in a process pipe to achieve this. However, using an excessive velocity leads to a high pressure drop and requires a greater energy input. Next, we will look at specific CIP programs. First, for a pasteurizer circuit. The program starts with rinsing using warm water for 8 minutes. This is followed by circulation of an alkaline detergent solution for 20 minutes at 75 degrees Celsius. Next, the alkaline detergent is rinsed out. Then a nitric acid solution is circulated for 6 minutes at 70 degrees Celsius. The system is then flushed with hot water for 6 minutes at 75 degrees Celsius. Disinfection is done with hot water for 8 minutes at 90 degrees Celsius. Finally, the circuit is cooled with cold water for 8 minutes. Another common program is for a circuit with pipes, tanks, and other components. This simpler program begins with a water rinse for 3 minutes. Then, an alkaline detergent solution is circulated for 6 minutes at 75 degrees Celsius. This is followed by a rinsing and sterilizing step with hot water for 3 minutes at 90 degrees Celsius. The cycle concludes with a cooling step using cold water for 7 minutes. Let's discuss how vessels are cleaned using CIP. The flow of CIP fluid goes from the CIP supply unit to a vessel sprayhead located inside the tank. The internal surfaces are cleaned by the spray impact or deluge from this device. The used solution then returns from the vessel via a CIP scavenge or return pump. There are different types of spray devices used in vessels. Static sprayballs operate with a high flow rate and low pressure. Rotating sprayheads use a low flow rate and medium pressure. For the most challenging jobs, cleaning machines use a low flow rate but high pressure to deliver a high impact cleaning jet. This slide shows an effective Alpha Laval rotary jet head tank cleaning machine, which is an example of a high impact cleaning machine that ensures all internal surfaces are reached and cleaned. CIP systems themselves come in different designs. The main types are single tank systems, two tank and multi-tank systems, and dual operating systems. Here is a diagram of a single tank CIP system, which uses one central tank for the cleaning solutions. This slide illustrates a multiple tank CIP system, often from suppliers like APV, which uses several separate tanks for different cleaning solutions like water, acid, and alkali. This is a diagram of a dual operating CIP system, which allows for greater flexibility, potentially cleaning two lines simultaneously or having one tank in recovery mode. The design of CIP systems can be broadly categorized into two approaches: centralized systems and decentralized systems. A centralized CIP system is a recovery or reuse system. It features a central station connected by a network of pipes to various equipment. A key feature is that the final rinse water is recovered and used as pre-rinsing water in the next cleaning stage. Detergent is also discharged only after it becomes too dirty, allowing for repeated use. It is important to clean the central tanks themselves at regular intervals. This complex diagram shows a centralized CIP system. It includes tanks for water, acid, and alkali, each with level sensors. The system has multiple pumps for supply and recirculation, heaters to maintain temperature, and sensors to monitor flow and conductivity throughout the cleaning process. In contrast, a decentralized CIP system is typically a single-use system with no recovery. It uses small cleaning units located near the process equipment they are designed to clean, rather than one central station. This diagram depicts a decentralized CIP system. It shows a compact unit with a buffer tank, a CIP supply pump, a heater, and sensors for flow and conductivity, providing a self-contained cleaning solution for a specific piece of equipment. There are advantages and disadvantages to each system type. A centralized CIP system allows for centralized handling and simplified utility distribution. It enables central recovery of milk rinses and neutralization of alkaline and acid solutions. However, it requires more space and has longer flushing times, leading to higher energy and rinsing water losses, which increases cost. A decentralized CIP system offers localized handling and is suitable for rebuilding or expanding facilities. It allows for simple collection of milk rinses and sometimes requires less space. With shorter pipe runs, it has lower installation costs, minimized rinsing losses, and shorter flushing times. A critical safety principle in CIP is to isolate the cleaning system from the production process. This is achieved using specialized valves like mix-proof valves or using flow plates. A flow plate creates a physical break between the process line being cleaned and the process line that is in operation, ensuring product cannot be contaminated by cleaning fluids. Finally, we come to the automation of CIP cleaning. Automation is typically controlled by a PLC or programmable logic controller, which is programmed with the sequence and timing for pumping solutions. Pneumatic valves are used at the inlets and outlets of tanks. A plate heat exchanger, or PHE, is used to maintain the temperatures of the cleaning solutions. Level in a tank is monitored by a sensor. Chemical concentration is maintained by periodic sampling or by checking electrical conductivity. And finally, sufficient pressure is maintained throughout the system to ensure effective cleaning. This diagram illustrates an automated CIP setup. It shows tanks for water, alkali, and acid, each with level sensors and concentrate lines. A heater uses steam to maintain temperature, and the cleaning solutions are circulated to the equipment to be cleaned. This slide shows a control panel for an automated CIP system, humorously labeled the Cleanzomatic 3000, highlighting how automation handles the complex cleaning sequences. We end with the references for this unit, which include essential handbooks from authors like Byland, Farfall, Hui, Kutz, and Saravakos and Kostaropoulos. These texts provide the foundational knowledge for dairy processing and equipment engineering. Thank you for joining us for this comprehensive overview of CIP systems. We covered everything from the basic principles of turbulent flow to the different system designs and the importance of automation. Understanding these concepts is vital for maintaining the highest hygiene standards in any modern dairy processing plant. Thank you. See you in the next class.